Thanks all. We will get to the last part of today with Jibran on QNickel. Thank you again, Aisha. And soon the video will also be uploaded, and you find all lecture slides from the last days already on Canvas and on the Discord channel daily schedule.
All right, good to start. Hello, everyone. Welcome to day 4 of Bronze plus Nickel. So the plan for today is to finish up where we kind of left off in the middle yesterday. We had done Deutsch-Joseph, we had done Bernstein-Vizirani. Hopefully all of that is fine. I didn't see any major questions about them online. And then today we finish up those 3 chains of algorithms by discussing Simon's algorithm, and then move on to discussion of Grover's algorithm. And that's particularly important for the connection with nickel, because in nickel, one of the key things that we're doing is an application of Grover's algorithm for solving an actual kind of interesting classical problem known as max cut. More about that tomorrow, hopefully, if you get there. All right, so first Simon's algorithm. So recall, we had started with Deutsch-Joseph, which was this promise problem on Boolean functions being either constant or balanced. We had moved to Bernstein-Vizirani, which was a generalization of that promise, in the sense that the promise was that the input function or the encoded function in the oracle will be one of the parity functions. Yes, there are Jupyter notebooks for all of those algorithms in bronze and nickel. For yesterday's discussion, it's essentially a nickel. And then today, the promise is being modified in a more interesting way. So first of all, to begin with, things are already more interesting in the sense that we are not looking at just a Boolean function, i.e. mapping n bits to a single bit. Rather, we are looking at functions that will map n bits to n bits. And then the function is promised to have this following property, which you can read off as there are 2 values that will map to exactly the same output, or the function is just a bijection. I.e., there's this, what we'll essentially end up formulating it as is that there is this Boolean string S, also of length n, such that the function f evaluated on a certain string x is going to equal the same function f evaluated on x parity this magic string s. And the goal is to find the string s. And this has cryptographic applications, which we can, you can look it up, and I can share resources on Discord as well. So the goal is find the string s for the function f that's encoded in B sub f. And note again that the circuit is really very similar to, again, Bernstein-Vizirani and Deutsch-Joseph. Obviously, one of the key changes is that because the function now is going to output n bits, we need to have n bits over here to encode, hold the output of the function. Yet at the same time, note also that we are not going to be using the phase kickback effect in some sense over here, right? Because this is not initialized to 1. First of all, it's not a single qubit. There are n qubits. They are not going to be initialized to 1 or flipped to the minus state. So we are not really using the phase kickback effect over here. All right. So let's build some intuition about this function, though. Let's consider this function, where I've particularly chosen n equals 3, and I've chosen one specific such function given by this truth table. And let's try to figure out by specifically evaluating this function's property based on this criteria to figure out what the string s is. So we know f of all 0 string, obviously, is 1, 0, 1. And from that, we can directly figure out by looking up just in the truth table, well, which other function input value evaluates to 1, 0, 1? Well, that's over here. So that means this is equal to f of x plus parity. Well, x in this case was all 0. Parity, the string s, which in this case actually will end up being just the string 110 itself as well. Because in this case, the function still evaluates 101. So we can pretty much have a good claim to conclude that s in this case will be 110. And you can actually verify this now, right? And I leave that as an exercise for you to figure out if f of 001 and so on and so forth evaluates to a certain output such that f of 001 parity 110 will have the same value. Let's do a quick check just for this. Well, f of 0, 0, 1 is 0, 1, 0. And 0, 1, 0 is also the value for 1, 1, 1. And that's exactly what you'll get as the parity of these two things, right? So we have identified that the answer for this particular f is the string s. We'd like to find this in general. This problem is going to be hard classically. You can do the argument in terms of the birthday paradox, if you've seen it before, in terms of you've got kind of a pool of size 2 to the n. What's the chance that two of them will map to the same kind of bucket? So this is a hard problem classically, such that you'll recall that Bernstein-Vizirani just needed linear number of oracle calls. Here we are going to need at least square root of 2 to the n oracle calls classically. And let's figure out what will be the complexity in the quantum case. It won't be as simple and trivial as it was in Bernstein-Vizirani or Deutsch-Jozsa, where you just needed a single oracle call. Everyone okay with the definition of the problem and what the classical kind of result is in terms of the complexity? All right, the first few calculations are relatively straightforward, just like last time. We've been doing them often. Hadamard gets applied to the first set of n qubits. You get the uniform superposition. So that's going to be written as 1 over square root 2 to the n sigma x, and these remain in 0n, right? And x, recall again over here, just to avoid confusion, is a length n bit string. You apply b sub f, we don't get the phase kickback effect. What do we get? We get f of x evaluated and stored in the auxiliary qubits. And so you write this off sigma x, f of x, right? You apply Hadamard again, you use our nice old identity from last time, that what happens if you apply Hadamard on some state x, and you get 1 over 2 to the n, sigma x from before, sigma y from the identity, minus 1 to the x dot y from the identity y, and your f of x remains as it is. Alrighty? Oops, finish. Okay. So that's complicated looking, right? So we are back to figuring out what are the probabilities going to work out for getting a right answer. Let's look at the trivial case. The one that, if you look at the problem, is the case when the particular string s is just the all zero string, right? There are two particular choices for s. S could be a really interesting magic string, in which case there are two unique values that get mapped to the same output, or the function is a bijection, in which case s is the all zero string. So let's work out that simple case first. What if s equals the all zero string? So if f is equal to the all zero string, we're interested in figuring out what will be the probability with which we get a particular string. So consider, right, we want to consider the probability of getting one particular string y from a measurement result over here. So we pull that y out and consider now what's left. And that's this everything else, 1 over 2 n sigma x minus 1 to the x dot y. And you've got your f of x. Alrighty? Oh, so in order to measure a particular y, I need to kind of apply the Born rule over here. That will be just obtained by taking the square of the norm of this vector. So I need to calculate 1 over 2 n x minus 1 x dot y f of x. And you can verify by just taking the inner product here that that's just going to be the uniform distribution. So in the case when the function is a bijection, I get a string that is uniformly distributed over all possible length n binary strings. And since this is the trivial case where f is a bijection, okay, so I just get a random string as output. Let's try to compare this to the interesting case where the function is not a bijection. So there is a particularly interesting s, string s. obviously we still start out with the same kind of vector in front of a particularly chosen ket y. But now we have this additional property that we know, right? That the function f has this property that it's going to map to the same output on two unique inputs. So let's use that information to modify this expression. So let A be equal to the range of the function f. If z is in A, right? So that means, first of all, z itself is also a length n binary string. But then this also means that there exist two length n binary strings. Let's call them xz and xz prime, xz and xz prime. Both of them are length n binary strings. And what will be true? That the function f will evaluate to z on both of them. F of xz equals f of xz prime, right? And in fact, what we can also conclude is that xz parity xz prime will equal this string s, based on the promise that we were given. So I can take this expression now and rewrite it using this information. That the summation can be written as not over all length n strings, but rather over the range of f, the range of strings minus 1 to the xz dot y, or minus 1 to the xz, let's write that nicer, dot y. And for both of these, the output will be the string z. Right, so rather than having kind of these sum over 2 to the n entries, I'm just summing over the summation over the range of f. And I've got these two inputs now, or two kind of phases now coming in, because on both of these inputs, xz and xz prime, the function was evaluating to the same string z. Right. And I can use this now to simplify my calculation a bit, right? So that's the expression we had. Let's go through kind of the fact that xz and xz are related by the string s to get this expression as 1 over 2n sigma z minus 1 to the xz dot y plus minus 1 to, recall xz prime equals xz parity s. Just plug that in over here. We've still got the same thing, right? And so that then again can be simplified to 1 over 2 to the n sigma z. Note xz dot y now occur in both places, so you can take that out as a common factor. And we've got 1 plus minus 1 to the s dot y left over here. And you've still got that z. So now we can do some kind of conditional reasoning on for figuring out the probabilities, kind of like how we did for Deutsch-Schoser. So s dot y is either going, it's kind of an inner product between binary vectors, right? Because s is a binary string, y is a binary string. So you just have this possibility that either s dot y equals 0 or s dot y equals 1. So if you're following along, what should be the probability over here if s dot y equals 0? And what should be the probability over here if s dot y equals 1? Well, s dot y equals 1 is kind of the simpler case, right? If s dot y equals 1 over here, you've got minus 1 to the 1. That's minus 1. This evaluates to 0. The anti-amplitude evaluates to 0. And so you get 0 over here. So you will never get a string as output from your measurement result such that its inner product with s is between s and y is 1. However, you will always get, with uniform probability, a string which will have inner product 0 with S. And so although you're not getting the whole string still as output, you're getting kind of this bit of information. We always get a string such that s.y equals 0. And this we use for the purpose of our classical post-processing, which essentially says, repeat our algorithm n-1 times. There's a bunch of details that I'll kind of leave out for you in the Jupyter notebooks in the classical post-processing. And so idea is you get a string y1, y2, up till yn-1, such that for the same string s is fixed, right? That's the string that we were after. But we now know s.y1 will equal 0, s.y2 will equal 0, and so on and so forth. s.yn-1 will equal to 0. And these are binary strings, so we need only do it for n-1 times and solve the system of equations. Obviously, one issue here will be that you need to ensure that these are all linear and independent y's, which if you do the analysis, you can verify that I'll still need only a linear number of iterations to guarantee that I repeat Simon's algorithm order of n times to ensure I get these n-1 linearly independent vectors, right? Once you have these n-1 linear independent vectors, you solve the system of equations to essentially allow you to solve for S. And so this gives you, for any error rate greater than 0, we can solve with error epsilon, at most epsilon, using order of n queries to B sub f. Right, so we need one oracle call for this, one for this, one for this, and so on and so forth. There's a bunch of classical post-processing that I'm kind of skipping over. It's discussed in the Jupyter notebooks, where you're essentially saying, all right, what if the y2 that I generated over here, or y3 that I generated, is not linear independent to the previous vectors that I've generated? Well, just repeat the algorithm again until you do get linear independent vectors, and you can show that that calculation only requires you to repeat this process still a linear number of times. So note what's happened over here. The classical query complexity was order of square root of 2 to the n, whereas the classical complexity is O of n. And so this allows you to have a much stronger argument of a quantum advantage in a practically interesting problem. And as mentioned yesterday, this insight over here about identifying almost kind of this periodic, not periodic structure, but a pattern in the structure of this function leads to also what develops into Shor's algorithm. Questions about Simon's algorithm? Modulo this bunch that we've skipped over. Everyone's good. Sum of x into 2 parts. All right, so we are going back here. We are not necessarily, so this is summing over all the possible binary strings of length n, right? But we note that over here, what happens, occurs inside the ket is f of x. And f of x, we have been promised, has this property that in the case when s is not equal to the all zero string, is not a bijection, there are 2 unique strings that will get mapped to exactly the same output. So let that output string be z, and consider the set of all such strings, which will constitute the range of f. So we say let the range of f be the set A. For any element z in A, we know, according to the promise, that there will be exactly 2 unique strings, xz and xz prime, for which the function will evaluate to z. So rather than summing over all length and binary strings, we say, all right, let's just sum over all strings in the range of A. For every entry in the range of A, I will have 2 unique strings, xz and xz prime. And so I get these two different entries for each of those two entries, right? So I will have exactly z occurring for both xz and xz prime. So that's why I can kind of put some of these amplitudes or combine these two amplitudes together in front of the kit z. And that helps us to kind of make progress in simplifying this expression. The distinctive characteristic of this algorithm, well, to begin with, one, the function is now not a Boolean function that's mapping n bits to a single bit, but rather to n bits. It's a classically hard problem where even in the probabilistic case, I need exponentially many oracle calls. In the quantum algorithm, it's not a a trivial problem either. It's not as if the quantum algorithm solves it with just a single oracle call like in Deutsch-Rosa and Bernstein-Vizorani. I still need to repeat the quantum algorithm order of n times. It's a probabilistic argument. There you say, all right, in the interesting case where S is not the all zero string, I get a string Y as my measurement result, which is guaranteed to have inner product 0 with S. And now I repeat my algorithm multiple times, each time hopefully getting a new Y, which is linearly independent to the span of all the previous Ys that I've generated. Once I've generated kind of n minus 1 linearly independent Ys, I've got a system of equations that I can solve for S and hence obtain my S. Right, so there's a bunch of non-trivial classical post-processing that I needed to do in order to actually extract my S. And that's something exactly then leads to stays with us for more complicated algorithms like Shor's as well. So there's a quantum subroutine, but then there's a reasonable amount of classical post-processing that I need to do to actually extract the results. Parity symbol is, think of it as XOR, the logical XOR, mod 2 addition, both are, I think, already good. So with that, now we move on to an algorithm with a slightly different characteristic to the previous three that we've seen. So for a reasonable time until kind of like 2005 or so, the two major classes of quantum algorithms were kind of amplitude amplification and, well, maybe 2005, we already had quantum annealing and adiabatic algorithms. So maybe up until 2000, let's say. You had kind of Bernstein-Vizorani, Shor, Deutsch-Rosa, all of these kind of classes of algorithms, and then which kind of belong to the abelian hidden subgroup problem. And then you've got these amplitude amplification protocols and algorithms, Grover's algorithm being kind of the key prime example of that. So the main algorithm that we do for today is Grover's search algorithm. It's discussed in bronze as well as partially in nickel with slightly additional details. Hopefully we'll get to both of them. And then tomorrow we see the application, because Grover is so general in terms of the problem it solves, we are able to then approach a large class of problems that benefit by using Grover as a subroutine. Yeah, so this slide should have come first. All right, so what is Grover? Grover is now saying you have some Boolean F. I don't know, I don't have any other additional promise over F other than the fact that, all right, over some entries it will evaluate to 0, i.e. over some inputs it will evaluate to 0, and over some inputs it will evaluate to 1. I don't know, I'm not giving any promise about how many entries it evaluates to 0 and on how many inputs it evaluates to 1. I just am interested in figuring out a string, an input string X, such that on that string X, I'm guaranteed that the function will evaluate to 1. In the literature and the discussions, you'll see this mentioned as unstructured search, searching for a marked item, i.e. the function is marking these items as keywords or key items that you want to look for. Sometimes it's mentioned as database search. We won't get in all the technical details about it. For us, it's sufficient to think about it as, all right, I've got a black box model that's encoding B sub f in my standard representation that we've been discussing so far. What I'm interested in solving in Grover's algorithm is identify a string X for which I know that the function will evaluate to 1. The function now is back to being a standard Boolean function, i.e. it evaluates to just 0 or 1 on every input. All right. If you think about it just a little bit classically, you can already kind of conclude that here, there is nothing, because we have no additional promise here about the structure of F, there's nothing better you can do other than just kind of a brute force search. Hey, tell me the value of F on this input, tell me the value of F on this input. And so and you need order of 2 to the n queries to solve this problem classically. Quantum mechanically, even though the advantage is not as great as for some of the other previous algorithms that we've identified, but yet it's a very generic quantum advantage that we get this quadratic improvement in the runtime, whereas previously you had 2 to the n runtime classically. Quantum mechanically, I get square root of 2 to the n or capital N. Right? Using randomized algorithms, classically, you can achieve the quantum bound, right? No. In general, Yash, your question is essentially about the two complexity classes, BPP and BQP, right? So randomized classical algorithms, quantum algorithms that are allowed error. So for sure, we expect that there are quantum algorithms which will not be in BPP. That is, BQP is bigger than BPP. Important question, how do we actually construct the f of x that we're interested in real world applications? We'll touch upon this a bit more tomorrow once we get into those applications. For the moment in our discussion today, consider f of x to be a black box. All right, we have it. How do we actually construct it for particular cases? We'll see tomorrow in one particular case, i.e. the max cut problem for graphs. All right, so for constructing Oracle, hopefully just stay with us till tomorrow. Yash, are you okay with the discussion regarding randomized algorithms versus quantum algorithms? Thank you. All righty, so what's Grover's algorithm? Here's kind of the specification of algorithm. And really, it's just step 2 that's the key step in this procedure. Step 1, we have got our initial n qubits initialized to all 0 state. As we've seen in all quantum algorithms, the first step, apply n-fold Hadamard, i.e. apply Hadamard to all your n qubits. So you get your uniform superposition. The non-trivial step of the algorithm, you identify this G, which is made of this bunch of specific logical gates connected together. We'll unpack this in multiple different ways in our discussion today. H is naturally still the Hadamard. You've got the Z sub F, which is essentially your oracle call for the F. And then you've got this particular Z naught over here, which really is kind of trivial. Z naught is independent of F. It's just a fixed transformation that says, hey, if the input string X is the all 0 string, introduce a minus sign in front of the ket, otherwise don't do anything. All righty. So that's your Z naught. So we now at least have a specification of all of these transformations. ZF is your standard oracle encoding F. H is your Hadamard. Z naught is this relatively simple transformation. You apply this interesting transformation to the uniform superposition that we constructed over here. And then there's this magic K that appears, which says, hey, apply G K number of times. And the whole task for us in analyzing Grover's algorithm and understanding Grover's algorithm will be figuring out what's the relationship between applying G K number of times. What should K be? And once we know K, obviously the algorithm is done. Apply G K number of times and then measure your results. Alrighty, so that's and the hope is that this then with high probability will be one marked item of the function. So superdense coding is kind of like a, I don't want to say a toy protocol, but it's not something as in, it's asymptotic, right? It's just something for 2 fixed constant bits. Whereas when we're discussing Grover's algorithm, we're talking about order of n inputs. So I'm not sure whether kind of in some weird way, superdense kind of boils down to, or Grover's algorithm boils down to superdense coding. But what we did see, actually, if you recall, we did between Deutsch-Schuster and Bernstein-Vizorani a particular special case of a balanced search for the parity function, in which case the function evaluates to 1, we were promised that the function evaluates to 1 on exactly 1 of the possible inputs. So that was kind of the base case of Grover for a single marked item in some sense. Right? So you can refer to the slides from yesterday, or we can take up the discussion later. All right, so recap, Grover's algorithm is initialize all 0, apply Hadamard, apply G K number of times, bunch of stuff in there. We'll unpack these and then just measure. Key thing, why do we or how do we figure out applying G k number of times. What's the relationship between this? That's what we need to now figure out. Questions before we now start unpacking G? Z is just a random alphabet here. Right, good question. Thank you for getting that clarification. Z here is not referring to the poly Z, also because these are now applied over a register of n qubits, right? Not a single qubit. So this is also not Z tensor n. H is an operation over a single qubit. That's why we tensor 10 times. Z naught and ZF are logical gates defined over n qubits, where ZF is defined essentially as an oracle call, and Z naught is just defined by this operation. Okay. All right. So we've got some bunch of useful information that we'll keep referring to on the side. You'll see why we've got this picture over here. And this is essentially what the circuit representation of what we just mentioned in the previous slide refers to, right? Your n qubit register initialized to 0, your Hadamard, your application of this entire G operator, which is this thing, and then you're repeating it k number of times, and then the measurement. All right. So let's identify this as my G. This is the G that we had, and we are applying it k times. All right. So where do we get started? Seems the setup is slightly more complicated than our previous algorithms. And the nice thing is an observation that we really are looking at binary output. So you can take all your possible inputs and put them in one of two possible subspaces. Either a string is good or a string is bad, quote unquote. Good, i.e. it's one of the strings on which the function evaluates to 1, or bad, if that's the case in which the string the function evaluates to 0 on the string. So we've got this identification as good subspace and bad subspace, or good strings or bad strings. How do you define them? So again, let's define this set A, which contains all length n binary strings such that f of x equals 1. Why these good? Naturally, why? Because these are the x's that we want to output. And let small a refer to the size of the set. And these are small a essentially then refers to the number of good strings. For Z naught x, so Z naught x is not actually dependent on f. F could be anything, and we are defining kind of a fixed transformation. Z naught of x is basically just a transformation that says, hey, introduce a minus sign in front of the all zero string. And we'll talk more about that as we go. So you can't really, we'll hopefully by the end of the conversation, it will be clear. We can't really say Grover will terminate once we found the string, because we are not kind of measuring at every intermediate step, right? We kind of are going to say, we do some pre-computation already to figure out how many times I should repeat the algorithm, after which I perform a single measurement. And for sure, there's kind of analysis to be done about, well, how many marked items are there, hence which determines how many times I should repeat the algorithm. We'll have more to say about this once we get there, right? So those are good questions that you have, and we'll just hold on them for a bit. I won't be able to answer them completely, but at least I'll kind of set up the base case for you in terms of how we figure out K in a special case, and then general case kind of follows from there. That's not like a very satisfactory answer, but hopefully it will get you started. And so B is a bad set of strings. So B contains all the strings X. They're still binary length n strings such that f of X equals 0 on those strings. And let small b be the size of this set. And we refer to these as the number of bad strings. And now the observation we have is that this uniform superposition state that we create right in the beginning over here, we can think of it as just a uniform superposition over all length n strings. But since our output can be thought of as either good strings or bad strings, we can now write it as summation over kind of states that span just the set of good strings and span the space of bad strings. What do I mean? Let's try to write it out. So I could define the state A, which is the uniform superposition of all the good strings. Well, that would look like something like this, right? X is in A. And so that's X. And similarly, the uniform superposition of all the bad strings. Right, so the key distinction over here is this is a summation over the good strings, this is a summation over the bad strings. And so and then the key insight is that at any point during the computation of Grover's algorithm, i.e. as we are evolving along the circuit, the state of my n qubits, my register, can always be thought of as a linear superposition of some alpha times good states plus beta times the bad states. And that's going to really help us simplify the complexity of the analysis. That really we're working in just this two-dimensional space, and that's what this kind of now picture is there for as well, right? So you've got kind of one dimension for the good, for the bad space, one for the good space, and somehow you're thinking of starting out somewhere on this vector, and you're hoping that as you apply G, and we'll prove that it is indeed the case, you are kind of rotating away or moving closer to the space of good states and moving away from the space of bad states. That's essentially the key idea of Grover's algorithm in this particular way of thinking about it. We'll give another perspective on it as well. Any questions on this kind of big picture of Grover's algorithm? It's just this superposition of good states and bad states, and we'll try to figure out how the amplitude over the goods in front of the good states changes and how the amplitude in front of the bad states changes, i.e. this alpha and beta. Okay. Actually, so to complete the answer to your second part of the question, we are not required to find all the X's that are marked. In the standard specification of Grover's algorithm, you're required to just find one such X. For sure, you can modify Grover's algorithm to then say, hey, I want to find all the items. Okay, but that's not what we'll analyze today. Okay, so then this uniform superposition that I created in the beginning, just for clarification, this looks like this thing, X over all strings. Based on my definition of A and B, let me just quickly write them down over here. This was 1 over square root of A sigma X in A X, and B was 1 over square root B sigma X in B X. So I rewrite now this uniform superposition, which is the state I have at this time step, into the state small h, which is just a mathematical rewriting of so Raja, we don't have to find all the x's. It suffices to find just one in the standard specification of Grover's algorithm. Hopefully my sound is okay. All right, so this I can now rewrite as square root of A over N, the good states, plus square root of B over N, the bad states. Okay. So what I've done is basically just take this uniform superposition and say, hey, I can kind of put them in two different buckets, the good bucket and the bad bucket, the good space and the bad space, and modify the amplitude accordingly in front to take care that it's still a uniform superposition. Now, the next step of Grover's algorithm is to say, hey, apply this entire thing, well, this entire thing actually, which we say is G, and that will be our next step to figure out what's the result of applying G to the state H, right? And so you'll see the benefit of writing down H in this form rather than this form. So we want to compute G of A, and we want to compute G of applied to B. Now, one thing that will be useful to just write down before moving forward with this calculation is note that this operator Z naught which has this specification, can be thought of as having this kind of matrix representation. Given whatever size of system you're working on, it will be just the identity matrix, except that the very first entry will be a -1, right? Because this then causes it to flip the sign in front of the all zero state and be identity in front of everything else. So we make this observation that Z0 has this matrix representation. If you don't writing it like writing it as a matrix with these ellipses in it, you can write it as identity -2 or 0, right? So this is new for some people. This is just the conjugate transpose of the ket in general. So this is essentially a row vector. So if you had 0 as this vector, as this ket, then this is this vector, row vector. And so the multiplication in this way creates a matrix, right? So this notation would be useful for the calculations that we'll do moving forward. Right, you see how the specification of Z0 is independent of F. It's just this trivial matrix with a -1 on the top left, and everything else on the diagonal is 1. Every other entry in this matrix is 0. So now we have everything that we need to compute G of A. Oops, not G of A, G applied to A. So G applied to A, well, let's just plug in everything we know. G is minus H tensor N Z0 H tensor N ZF applied to the state A. Well, let's observe this first, that ZF with a minus sign applied to A. What is that thing going to be? And we'll use this bit of information over here. Minus Z sub F applied to the ket A. Well, if note, by definition, A contains all the strings X's for which F of X evaluates to 1. So Z of X, Z sub F applied to X will yield -1 to the 1 X, agreed? Well, -1 to the 1 is -1. But now over here, I'm computing minus Z sub F applied to A. So the two minus signs will cancel. And the Z sub F applied to A gives me just A back. So I make this observation, which simplifies my stuff over here, that, hey, I just actually need to calculate H tensor N, Z0, H tensor N applied to A. Right? Good. Well, now, what is H tensor N, Z0, H tensor N going to look like, given that I already have a nice representation for Z0? So that's going to be H tensor N. Recall from a previous calculation, this is just I minus 2, 0, 0. And this is also H. Right? That seems still something nice that we can calculate. Bring in the H's from both sides in. The part where they get applied to the identity, they cancel each other out. So I'm still left with identity minus 2 HN applied to the all 0. Hey, that seems like something that I know how to calculate already. So that's cool. H applied to all 0 from the right hand side, H applied to all 0 from the left hand side. I could write it as a uniform superposition sigma X, but recall, I already have a nicer name for it. I call it the state H. So this is going to be just equal to identity minus 2 the state HH. That's nice. So kind of complicated looking thing has a nice simple representation. So I now need to apply this thing, or I can plug in this thing over here to apply to A. Okay, so let's just do that. GA is going to equal I minus 2 HH applied to A. Again, one is trivial. Identity applied to A just gives us A back again. Minus 2 H H, and then the H with A, and you see the benefit of the Ket representation, hooks up with the A to make this inner product. So you've got H, and you've got the inner product between HA. But this is something we already know how to easily calculate, right? Because H is the superposition between A and B. A and B are orthogonal to each other because they are just kind of summation over binary strings of length n. Each binary string is orthogonal to each other. So when you're taking the inner product between H and A, the B part in H will kind of give inner product 0. You essentially get exactly this square root of A n kind of contribution. And so this can be then simplified as A. Someone wants to fill in the blank on Discord. What should I write next? Have we been following along? Yep, someone's following along. 2 square root n, excellent, minus 2 square root of A over n. And then I've got the Ket H left, right? So I can literally plug in the Ket H, which is square root of A over n A plus square root of B over n B. Cool. I can simplify all this, and that gives me, I think, yeah, 1 minus 2A over n for A minus 2 square root of AB over n for B. Excellent. So we have applied G2A and gotten kind of a nice update of the amplitude. So we can observe, right? So what has happened is that the previous superposition that we had, the amplitudes in that superposition have been modified by application of G. We'll soon see that they are being actually updated in a very nice way. So we know that we've calculated that G of A results in 1 minus 2A over n A plus 2 square root of AB over NB. And through a similar calculation that I recommend you do, you can verify that G of B is going to be 2 square root of AB over NA and minus 1 minus 2B over NB. Right, so we've done some transformation. We know what G of A does. We know what G applied to A does. We know what G applied to B does. Let's try to write it down as a matrix because it's just going to be a 2 by 2 matrix, right, in terms of A and B. So imagine the labels of the headings are, this is B, this is A, this is B, this is A. So essentially all that I'm doing now is taking these 4 entries and thinking of G as a matrix transformation and writing down kind of that matrix. So G is then represented by this matrix, 1 minus 2B over n, right? That's the amplitude in front of G mapping B to B. So that's the entry, that's over here. Similarly, G getting mapped, this one will be minus 2 square root AB over n. This I should have written in black, but fine. This is going to be 2 square root AB over n, and this is 1 minus 2A over n. But perhaps you already see the pattern here, but if not, you can do, let me do one more step and note that this matrix M equals square root of B over n minus square root of A over n, square root of A over n, and square root of B over n squared. Alrighty. So yeah, this one's positive, but this one is going to be negative, right? Oh, this one introduces, so I might have messed up a minus sign somewhere. I'll definitely check that and write that down, correct that later. But if you allow me kind of some error in a minus sign, the observation is that this matrix squared will give me this matrix, which essentially are the entries that correspond to the transformation over here. And this is nothing more but what looks like very easily the rotation matrix, a 2x2 rotation matrix, if you parameterize this as cosine theta and minus sine theta. And that gives us the nice geometric interpretation that all of this work over here in terms of our good and bad spaces has resulted in this picture that we had to begin with, that it's causing a certain rotation. Why is it 2 theta over here? We'll assume where that is coming from. Well, you see that, well, applying M once is applying this matrix twice. And so if I make this cosine theta, then squaring this matrix essentially results us in applying rotation by 2 theta. Right? So that's where the 2 theta was coming from. So we do the parameter, again, one more parameterization. Let sine theta equal square root of a over n, and cosine theta be equal to square root of b over n. And that results in our initial superposition of h to be equal to cosine theta b plus sine theta a. Cool. Which also means now that I can now bring in what was hard previously to figure out, well, how many times would I need to apply k, and how do I figure out what's the effect of applying g k number of times? That's what we've made progress towards now. After k applications of g, the state h will be updated to well, we already have the theta parameterization or theta appearing before doing any application of g. So this will be theta plus something or theta plus something. Every single application of g is a rotation by theta or 2 theta, right? And you do this k times, so you get a multiple of 2k. And so you get the state cosine 2k plus 1 theta b plus sine 2k plus 1 theta a. All right, so that's the nice kind of final evaluation. We're not all done yet, but we kind of have now k finally appearing in an analysis, that if you're following through with Grover's algorithm by applying g k number of times, I still don't have a bound on k, right? But if I apply g k number of times, I will have the state evolves to this thing. And already you can see what will be an issue with this, right? So since I'm keeping, after every application of G, I'm rotating, I will need to have some kind of optimality guarantee that, hey, for a particular choice of input distribution, in terms of how many inputs get mapped to good, how many times should I rotate to optimize how close I am to get the probability of something good out rather than something bad out. And that's exactly what will happen, right? So let's do that analysis. I want this to be as high as possible, right? How do we get the 2k plus 1? So you agree that this is the state h, which was the state we had obtained over here. Our conclusion from the previous slide is that every single application of G is going to be a rotation by this matrix twice, because we have said a single application of G results in this transformation, and this transformation I've asked you to verify is this matrix squared up to some minus sign issue that I might have made. And so if I apply G once, I get a rotation by 2 theta. And so if I apply G k number of times, I will get a rotation by 2k theta, or 2 theta k times, right? So I had this plus 1 is for the original theta, and then applying G k number of times gives me this 2k factor. So that's the 2k plus 1, right? So I would want this is where, right? So I want to maximize this thing in terms of making this as close as 1. And here you see kind of our generic intuition about amplitude amplification thing, right? That we are doing constructive destructive interference or what have you to get the amplitude of the right answer as high as possible. So we would like to solve for the case where we can claim that sine 2k plus 1 is approximately, or theta is approximately 1. That's what we'd like. So we want to solve for k with that criteria. So since we want sine 2k plus 1 times theta to be approximately 1, so we get k to be approximately equal to, and takers. So this would imply that 2k plus 1 times theta should be approximately equal to pi over 2. Given that, then we get k should be equal to pi 4 theta minus half. Recall that we have made the observation that sine of parameterization, that sine theta is equal to square root of a over n. So theta then will be equal to sine inverse of square root of a over n. And now we start making additional assumptions. We are solving for the asymptotic case. So the asymptotic case means that the function, the n tends to infinity, or n is large. So if small n is large, then 2 to the n, 2 to the small n, or capital N is definitely large. So, and then additional simplification we can make is assume, just to simplify analysis for the moment, assume A is 1. A is 1 would mean that we are making the assumption that we've only got a single marked item. Intuitively, kind of, sort of, it's the hardest case in some sense, right? We are looking for a single item in a set of size 2 to the n. If there are more marked items, we hope to run into them faster. So let's, for the moment, do the analysis for the case where we've got a single marked item and we assume large n. Both of them are reasonable kind of assumptions. So we get theta to be approximately square root of 1 over capital N. So the sine inverse kind of, we can drop off, right? Because n is large. So sine inverse of square root of n will be also 1 over square root of n. You plug this back into what we have over here, and you get then that k should be equal to pi square root of n over 4, approximately, right? Sure, you have floors and whatnot, but this then is our proof of our original claim that we started out with. So what is this saying? This is saying, what was k? K was the number of times I have to apply G in this circuit. This is saying k has to be order of square root of capital N. So if I want the amplitude in front of A to be approximately 1, assuming that the database is large, that the function is over a large number of bit strings, then, and there's only a single marked item, I've shown, or we have concluded, that order of square root of n iterations, i.e., applying this procedure square root of n number of times, will give us, with high probability, 1 marked item. Questions, queries, concerns? And I think I'll also kind of stop here and take questions, and also stop here for the day, because there's a second perspective of Grover's algorithm, which, rather than doing today, I can start from tomorrow, so that also leads into the application of Grover's algorithm to max cut. So we'll take a pause here for today, and I'll take questions where we are concluding that Grover's algorithm requires order of square root of n queries for a single marked item. If there are more marked items, then there's classical post-processing kind of arguments that allow you to conclude just a reasonable modification of how you're running these iterations will still suffice. And I can share resources for that on Discord. But the key quantum part is exactly done by doing the analysis for a single marked item. Thank you.
Fantastic. Thank you, Jibran. I will share my screen with the canvas as usual for you to point out which quizzes and exercises can be done while everyone has a chance to ask more questions on Discord. Here the canvas. We are really in QNickel now, where in the Get Started section is also pointed out where you can download the exercises via GitLab. But you see here the overview of notebooks for the exercises. So far, we got up to Grover's algorithm revisited, right, Jibran?
Yeah, well, so the revisited part is exactly what I'm planning to then do tomorrow. So I've done Grover's algorithm, the revisited part, then I'll start with tomorrow. In terms of the quizzes, it's easy also as well now. So if we look at the quizzes, we've done Simon's algorithm.
Okay, so to be clear, for exercises, Simon's algorithm is included.
Right, so the quiz for Simon's algorithm now people can also attempt. So that's 1.4, the assignment for Simon's algorithm. And if you've done the tutorials for programming, then the intro to search part should also be something that you should be able to handle. Grover's search, we hadn't done from bronze. So now the bronze part of Grover's search, you can also do. So that's QBronze quiz number 5, quantum search algorithm. That's something you can do now. The Grover's search part from QNickel is something that I recommend you attempt tomorrow after our discussion of Grover Revisited.
Excellent. And the dates will be added, the session dates will be added to the quizzes. So then it's really clear. And in the daily schedule, that will also be added. Thank you. Returning to Discord to see if there are more questions there.
The black box is an issue for the performance of the algorithm. So yeah, so we'll try to say more about it tomorrow in a bit of detail. But yeah, if you assume, and there are multiple different issues related to it, right? So if you assume it's not a black box, then you can open it up. Kind of the advantage kind of goes away, right? Because the classical algorithm can also look at the structure of the oracle, and well, so can the quantum algorithm. But then classically as well, you get kind of much better possible algorithms than what are possible with just black box approach. And that is a concern that recently happened in a popular kind of article that was published. However, we are categorically working in our current specification in the black box model, where we do have this separation that classically you have order of 2 to the n, whereas quantum mechanically you have square root of 2 to the n. Does this still work? That's exactly what we'll see tomorrow, in the sense that in a special case where we look at a problem on graphs for max cut, we see how to construct the oracle such that we can actually work or use Grover. And that's kind of what we started out in the beginning with as well, right? That Grover can be really thought of as a very generic subroutine that can be applied to many problems. So you, for example, when we discuss computation complexity, you take most NP-complete problems, and Grover's algorithm can be used there as a subroutine to get this quadratic speed up. But given that the best known algorithms over there already 2 to the n, order 2 to the n, getting a quadratic speed up still remains an exponential algorithm. So it doesn't really make too much of a difference in very quote unquote terms. Thank you. All right. The rest, we just make a measurement and read the string. Yeah. So let's say we are working under the assumption where there was a single marked item. We figured out the k based on this, did the application of g that many number of times, and then do a measurement. And with high probability, we've got the right x. And that verification is easy to do, right? Let's say, you know, we were unlucky and the x that came out was not corresponding to a marked item. We can easily verify that by a single oracle call again, that, hey, what does f of x evaluate on this? And if you were unlucky, just make one another oracle call, and then you can do the probability analysis that you just need constant number of repetitions if you're really, really unlucky to get with high probability the right answer. So order of square root n works out.
To conclude the session, who has a personal or a research-related question for Jibran? In the meantime, another question for you from Oxy.
Yeah, Oxy, when you're talking about probabilistic algorithms, exactly kind of, you can think about it as, hey, we can get the probability to as good as you like after square. So exactly the answer over here is we can get the probability of success to be as high as we like with only square root of n number of iterations or applications of the oracle. Is Jibran a researcher? Yes. So so in fact, the previous discussion today about with Aisha is something particularly close to my heart, because my focus in quantum information research is actually on non-locality. So stuff like CHSA, GHZ, non-local correlations, that's the focus of my research. how did you get into quantum information science? So I started my undergrad in 2000, and I took my quantum computing course in 2001. Didn't really understand most of what happened there, and kind of already got stuck there that, hey, here's something I don't understand. And so since then, I've been trying to understand quantum computing. That's how I got stuck with it. Yes, so I'll try to share a couple of resources. I owe you kind of resources from 2-3 sessions now. So I'll try to share a long list of resources, hopefully by tomorrow. All right, so Ron, exactly, practical use of Grover. Hopefully we'll see tomorrow. But yeah, so the idea behind both Grover and Shore is that we like to have lots of qubits to be able to kind of use them, right? So that stuff, exactly, that will be, that should lead to questions for your next week. So, you want to talk to the hardware people and ask them, what are the concerns, what are the issues in terms of getting lots of qubits?
Yeah, we will have very much of that, including in a hardware panel where the different qubit modalities can compete, trapped ions, superconducting circuits, everything. Thanks a lot, Jibran. Tomorrow we will have the last session with you, although there might be some time also next week for Q&A. Stay tuned, everyone. Tomorrow, extremely interesting keynote on post-quantum cryptography, the threats of quantum computing. Then continuing with QKD and with Jibran. For now, the WOMANIUM team will stay on for 10 minutes to answer general questions. And everyone else who doesn't stay on now, thank you very much for the interactive session today. Looking forward to seeing you tomorrow, and we will be in touch on Discord. Thank you very much.
Thank you.
And right now, we still have the team here. Lindsay is here, Madalina, Raj, Vardan. Great, I can see videos of participants. Thank you, Fatime. Thank you, Natalia. Wonderful having you all here today. Oh, and Dawal from India is asking, who is the hackathon king? Please speak up, Vardan, and share some of your tricks.
Hey, everyone. Yeah, I'm the so-called hackathon king. It's a really good title to have, but honestly speaking, I've participated in way more hackathons than I've actually won. But yeah, it's a great exercise to test your skills. So I would recommend everyone who is starting out in their journey in quantum to participate in as many hackathons as you can and always try to win.